Oxynitrides are exciting materials, but their chemistry is often confusing. Let's quickly see how they form and why ambiguity arises. Oxynitrides begin with a metal precursor and a nitrogen source. The synthesis pathway determines whether oxygen or nitrogen dominates. In soft urea and salt gel routes, nitrogen incorporation is limited, so the product remains oxygen rich. By adjusting nitrogen gas flow, and the oxygen to nitrogen ratio becomes tunable, especially in controlled thin film synthesis. Techniques like sputtering, laser deposition, and ALD offer precision, but phase purity and scalability remain major challenges. For nitrogen-rich oxynitrides, ammonolysis is widely used, achieving higher nitrodation but often introducing instability. Here is the key issue. The word oxynitride is often used loosely, covering very different material realities. A material may be just nitrogen-doped oxide, a mixture of oxide and nitride phases, or a true single-phase oxynitride. Even when diffraction looks similar, the underlying chemistry can differ completely, making identification difficult. So, resolving oxynitride ambiguities requires careful terminology, bulk plus surface analysis, and strong structural evidence. Oxynitrides are powerful, but only when we know exactly what we have synthesized. This schematic highlights the key uncertainties in understanding oxynitrides, where similar diffraction signatures can mask significant chemical and structural differences. It emphasizes challenges such as distinguishing oxide-dominated versus nitride-dominated character, identifying single versus mixed phase, resolving surface versus bulk oxygen-nitrogen distributions, and accounting for composition gradients and varying metal stoichiometry. Overall, it illustrates that oxynitrides with comparable structural fingerprints may still exhibit different composition and properties. This schematic summarizes combined structural and surface sensitive characterizations help resolve ambiguities in oxynitride materials. XRD probe bulk crystal structures, STM provides atom level compositional mapping, and XPS reveals nitrogen distribution and depth profiles near the surface. Integrating these techniques enables clear distinction between oxide, nitride, and true oxynitride phases and avoids misinterpretation from any single method alone. Understanding oxynitrides requires looking beyond diffraction and nitrogen content. By combining structural and surface sensitive tools, we can finally distinguish oxide, nitride, and true oxynitride phases and design materials with confidence rather than assumption.